So we saw RLC series circuit and we saw RLC parallel circuit. Now, if in a series circuit R is very small, almost equal to 0, what happens? This is gone. So this is like this. Or in this circuit we have R very large, infinite. So then this is gone. So in both these cases what we finally get is this circuit. This is a tuned circuit, a very important circuit that you find use in electronics. This is LC circuit. Through this circuit we are able to tune this circuit using the values of L and C. We are able to get a particular frequency that is used in communication. So this is LC circuit. Okay, let's say this voltage is V across this. We'll analyze this. So if the solution in the Laplace transform mode is e to the power st, as we have already seen, what happens? You remember the equation? It was d2v by dt2 plus 1 by RC. See, 1 by RC into dv by dt, and then we had 1 by LCV equal to 0. This was for parallel RLC circuit. And what I told you in the start only, that for a parallel circuit R tends to infinity. So when R tends to infinity, this is gone, this is 0. So the equation is this only, 1 by LCV. So if you take Laplace transform, you will get S square plus 1 by LC equal to 0. So the characteristic equation is S square plus 1 by LC is equal to 0. So this is S square equal to minus 1 by LC or J square 1 by LC. Okay. So from here what you get? You get S is equal to plus minus J 1 by root over LC. So you can write it like plus minus J omega 0, where omega 0 equal to 1 by LC is called the resonant frequency of the circuit. Okay, so you get the concept of resonant frequency. This omega 0 equal to 1 by LC is the resonant frequency. Okay, and from here what you get is the solution will be V equal to A1 e to the power S1t. So S1 is j omega 0t, and then A2 is the second root is e to the power minus j omega 0t. Okay, so this is the solution. And in terms of cos and sine waves, you can write B1 cos omega 0t plus j B2 sine omega 0t, the way we did in the last section. If you do like that, you will get this equation. So you should keep this equation for LC circuit. Actually, what this equation essentially means, that the result is a non-decaying wave of cosine and sine waves. Non-decaying means this wave does not decays. Once started, it will continue to infinity. But what happens in actual circuits? You do have a little resistance. Even in the inductor circuit or in the capacitor circuit, you very well know there is small resistance. So that small resistance actually decays the circuit. So you have oscillation and then it decays. It depends on the value of R, that after what time the circuit will be 0. The voltage or the current the response will be 0. That is, voltage or current will decay to 0. So this is the theory part of LC, LR, RLC circuits in series, in parallel and all. Now we will see some questions, some problems to solve these, solve real circuit problems. Right. Now we will see some problems. We will take some problems and understand how by these concepts we are able to get the voltage or current across capacitors or through the inductors in a circuit. Let's see an example. This is RLC circuit in series. So what do we have? KVL. It will be 2i plus L di by dt, that is 5 di by dt plus, let's say, Vc, the voltage across the capacitor, equal to 10 volts. Okay, so this is the equation. But what is I? It is C dVc by dt. Okay, so from here what you get, I is equal to C. C is 1, so it is dVc by dt. Now if you put it in this equation, what do you get? You get 2 into I, that is dVc by dt, plus 5 into di by dt, that is second derivative of this, d2v by dt2, plus we have Vc equal to 10, or if you divide throughout by 5, the equation that you get is d2v Vc by dt2 plus, this is 2 by 5 dVc by dt plus, this is 1 by 5 Vc equal to 2. So this is our equation. This we have done using RLC when we were analyzing the circuit. Now from here what you should understand is, we have done this RLC, simple RLC in a circuit. That was a natural response, and here we have a voltage source, that is a forced response. Now from this equation you can see that there are two parts. First is, when this is equal to 0, it gives the natural response, and this equal to 2, this part gives the forced response. So we have the natural response. Let's do the Laplace transform here. Laplace transform, let this Vc be given as a e to the power st, as we had done. So from here we get the correct, I'm directly writing the characteristic equation. For natural response, this will be equal to 0. Okay, that is clear to you. I'm writing it here, d2 Vc by dt2 plus 2 by 5 dVc by dt plus 1 by 5 Vc equal to 0. This gives the natural response. Okay, so from here what you get the characteristic equation, this into the characteristic equation equal to 0, that we have done in RLC circuit analysis. So this will be R by s square plus 2 by 5s plus 1 by 5 equal to 0. Okay, now I am rubbing this part. Or before rubbing, see, this is, I told you this is the forced response. So when we'll be talking of steady state, this dVc by dt, that is change of voltage with respect to time, will be 0 in case of steady state. Therefore this will be 0. So Vc will be equal to 2 into 5, 10. So our Vcf from this equation only is equal to 10 volts. Or you can see in the steady state, what happens? Current will stop to flow. This will behave as an open circuit. Once it is open circuit, this voltage will be here. So this Vcf is equal to 10 volts. So now I am rubbing this. So this is our equation. From here what do we get? S1 and S2. This will be minus b plus minus under root b square. B square is this 4 by 25 minus 4ac, 4 by 5. See, 4 by 25, 4 by this is, so this is negative. So what do we get? From here what do we get? When this is negative, we know this will give a complex conjugate. So if you work this out, the answer will be minus 1 by 5 plus minus j2 by 5. Okay, so what do we get? Finally our equation Vc, finally Vcf. So Vc, finally we get Vn plus Vcn plus Vcf. Vcn, what it is? It is you know, a1 e to the power this s1, that is minus 1 by 5 plus j2 by 5 into t plus a2 e to the power minus 1 by 5 minus j2 by 5 t plus Vcf, that is 10. So this is your equation. Or if you take this e to the power minus 1 by 5t out, what you get is b1 cos 2 by 5t plus b2 sin 2 by 5t. Okay. So how do we get the result? Not the result, these constants. See, we have, let's say, our initial condition, that is Vc0 plus and I0 plus for the inductor. This is 0. Okay. So what we'll do, first of all, let's put it here. So at t equal to 0, what happens? This is 0, this is 1, this is cos 0 1, b1 plus sin 0 0. So what do we get from here? No, we have missed one thing, this plus 10 we have missed. So this is this plus 10. So from here what you get, b1 is equal to minus 10. Clear? I have put this condition. Now what we'll do, we'll do dvc by dt. We'll take this value and we'll put at t equal to 0, vc is equal to 0 in that equation. When you will do that, you will get the value of b2, because you have the value of b1, and b2 that you will get is minus 5. So finally the answer will be b2 is minus 10 minus 5. I am putting minus here. So in place of b1 we can write 10, and in place of b2 we can write 5. So our answer is this, vc is equal to this thing. Okay. So since we have a complex conjugate roots, we know this is underdamped. The response is underdamped. Clearly, so in this way we solve practical questions.